Hello and welcome back to the video lecture series for Introduction to the Art of Programming Using Scala. In this video, we're going to take a little detour and talk about big O notation. This is an asymptotic notation for kind of how algorithms scale. And I've talked about this before in some videos, most notably when we did sorts. And we talked about the fact that sorts we called them big O n squared. And that was to say that how much work they did scaled as the number of objects squared. And I want to bring this back up because it winds up being significant to us in the area of stacks and queues. And in particular, what we're going to aim for is all of these operations, because the stack and the queue are so simple, we are going to put the requirement that these have to be big O of 1. So I guess I could put a comment in here. Whoa, that was weird. Require all operations be order 1. Okay. Now, if you take an analysis course, you'll get into the details of what exactly. It turns out big O isn't the only notation for these things there. It actually specifies a non-type tight upper bound on behavior. So things could be lower than this. There are other notations, a big theta for a tight bound, a little o for a lower bound. Anyway, those aren't really significant to us. Most of the time, in part because it's easy to type on a keyboard, we will wind up talking about the big O notation, and it's generally sufficient for what we want in this class. So what does it mean for something to be big O of 1? Or in the case of our sorts, we said our sorts were big O of n squared. Okay, what does that mean? Well, the mathematical definition of this is that if you count how many operations are happening of a certain type when you call a function or run an algorithm, whatever, that number winds up growing more slowly than whatever function it is that you have beyond some certain point. And in particular, so if I have some function f of n, and I want to say that g, a different function, is big O of f of n. What that implies is that there exists a c and an m such that c times f of n is greater than g of n for all n greater than m. Okay. Now, that's kind of might be challenging for you to think of. It's probably best to view this as a plot, and this is a plot that's taken from the textbook. Okay. Here we have this g of n. This is intended to be ragged here. Okay, this isn't a perfect curve. This would be counting how many operations we're doing. In the cases of our sorts, we were generally talking about comparison operations. We could be talking about memory move operations, whatever it is that we want to deal with, and it could be multiple operations. We're kind of packing them together. But typically, as your size of your input gets bigger, this grows, or at the very least it stays flat. And then we have some other function f. Now in this case I've made it so my f happens to looks roughly like a quadratic curve. And we don't care just about f, we care about this c of f. And so what we're saying here is there is some point m, you'll notice the m here on our horizontal axis, and beyond that point m, c times f of n is always greater than g of n. No matter how far out you go, going out to infinity, this dotted curve will always be higher than the bold curve. Okay, that's what it means to say that g is order f of n. Something to notice here, this c could be really huge. Okay, this is an asymptotic analysis. It really only matters for very big n, in particular n bigger than whatever our value m here is. It doesn't matter down here. It really doesn't tell you anything about small input sizes. Okay? It only matters for the large input sizes. and we throw away multiplicative factors. Turns out we can also throw away lower order terms. So there could be other things in here that just, so if we have n squared, there could be a linear term and a constant term, and they're thrown away because they don't really matter. So when we say that something has to be order 1, what that really means is that as the input gets bigger and bigger, the amount of work that we do doesn't grow. Okay, so I do the same amount of work if I have 10 elements as I would if I had 10 billion elements. And that's our goal for the stack and the queue. So we have to make sure that all of the implementations that we write for our stack and our queue follow that simple rule. And so we're going to come back in the next video and we're going to implement our stack using an array, and we'll talk about how we can make sure that everything in it is order 1.